All right, good morning. So I'm pleased to be here today to talk to you about the Kepler mission and some of the data challenges that we've had with respect to processing the data to find small planets. I'd like to thank Michael for putting this all together. It's been great working on the book in my spare time on the weekends when the kids aren't sick, that kind of thing. Anyway, this is a real pleasure for me to be here because it's, I usually go to astronomy conferences, and it's really great to see people really into data analysis, and that's where I find most of my pleasure. Okay, so I do work for the SETI Institute. The Kepler mission is a Discovery class mission that was selected back in 2001. Over 3,000 people at Ball Aerospace actually worked on the mission from the proposal through the design, development, and then delivery of the flight segment of the spacecraft and instrument. And there are several dozen people on the science team and the associated collaborators, and lots of institutions. So I do work at the SETI Institute, but we have SAO, LAS, Ames Research Center, which is where we manage the mission right now. JTL managed to build up, and the Space Telescope is where our archive is. So I encourage everyone to go and download data since we've got the first 120 days out there already. Okay, so today's talk, I'll give you an overview of the Kepler mission and the science pipeline that processes the data. I'll talk specifically about transiting planet search, about the algorithm we've chosen that allows us to find transit signatures in the data. And I'll talk to you about one of the challenges that we're grappling with now and an approach that we're developing to handle this particular situation where the functionality isn't quite what we, or performance isn't quite what we want. And then I'll follow up with some conclusions. So, at any rate, Kepler is a 1.4 meter telescope. It's got a 1.4 meter primary mirror in the back end here. It's got a 0.95 meter aperture, and it's in an Earth-trailing Spitzer-like orbit. So it's in its own orbit around the sun. That is very important because that puts us in a very benign environment where we don't have perturbations like low Earth orbiting satellites have with going in and out of the shadow of the Earth. And so we don't have large thermal excursions. And we don't see light scattered off the Earth or from the Moon, which low Earth orbiting satellites do as well. So this orbit was specifically chosen so that we could achieve our required photometric precision of 20 parts per million in 6.5 hours. So to give you an idea of what that means, from the ground typically people get 0.1% or a millimag. And on 4 meter class telescopes, if we work really hard, you can drive that down maybe by an order of magnitude or so. But the signals that we're looking for here are 100 parts per million. Earth transiting the sun is 84 parts per million for central transit. So we're talking about really small signatures. And you also are fighting the day-night cycle. If you're trying to do this from the ground, the stars are only up, right, at most 12 hours a night. And most of those hours, or many of those hours, aren't photometric. You've got weather. So we really had to go to space to do this. So here's our field of view. We also have to look at a lot of stars because we're looking for transits, occasions when the planet crosses in front of the star from our viewpoint. And the chance of that alignment is the size of the star divided by the size of the orbit. So we're talking about a sun-like star with a diameter of 1% of an AU, and you're looking for planets that are at 1 AU orbits. That means that you have about a 0.5% chance of seeing that planet transit that star, because you don't know how the orbits are oriented, right?
What's an AU, John?
I'm sorry?
Tell them what an AU is.
Oh, okay. So an astronomical unit, an AU, is the distance between the Earth and the Sun, right? So we're in a 1 AU orbit about the Sun. So that's why we have 105 square degrees in our field of view that are unvignetted. We actually have almost 116 square degrees on silicon. And I also drove the design of the telescope. We needed a telescope that could have a large field of view. So to give you an idea, our field of view is about the size of your palm held at arm's length, whereas the field of view for the Hubble Space Telescope is about a grain of sand held at arm's length. So it's a very different problem. We're not trying to make pretty pictures. Our object is to measure the brightnesses of all these stars over time. Because we need a lot of stars, we have a large field of view, and indeed we have 150,000 targets on our planetary target list. And we observe at any given time up to 165,000 stars. Those other 15,000 are for guest observers and science team targets that allow us to do control studies and to study other populations of stars that are of interest to us. So anyway, we also chose the field of view to be very dense star-wise because we wanted to have lots of sun-like stars in the field of view. So that means you need to look near the galactic plane And if you're interested in doing follow-up for NASA, most of its assets available for follow-up are in the northern hemisphere. So it turns out that CESS is basically the best bet for this mission for all those reasons. So that's what drove us to choose this field of view. Okay, so it's a baseline for a 3.5-year mission. We have enough hydrazine that we could go out as long as about 10 years or so. And I'm hoping that we last that long. As long as things are working well, I think they'll keep us going. Okay, it's broadband, white light. Some recent Kepler news. In January, we announced the first confirmed rocky planet, Kepler 10b. This is the first planet that's unambiguously made of rock. It's 1.4 Earth radii. It's in a 0.8-day period orbit about its star. This was very exciting indeed. There are other planets that may be rocky. Corot 7 is the first example of something that's likely to be rocky, but the error bars, the error ellipses on its density, on the mass and size are really broad, and so it's less and less likely now after several years that it's actually rocky. But you know, some people still have their bets on. Anyway, back at the beginning of this month, we announced that we've identified over 1,200 new planetary candidates in our data. And most are closer to Earth in size rather than close to the giant planets that have been previously discovered. So most are smaller than Neptune's. And indeed, 68 are less than 1.25 Earth radii. So, and 54 are in or near the habitable zone of their star. So for the first time in history, we have a sample of Earth-sized planets, and we have a sample of planets in the habitable zones of other stars. So this is proving just, I think, the tip of the iceberg in terms of the watershed that Kepler is going to provide to the extrasolar planet community. Question here. Yes.
Just to get things in perspective in my head, before January there were known, I think, only 500.
Right about, right, that's right.
So that's a massive, that's been a huge increase.
This potentially triples the number of known planets. Now, these are candidates still, because although we have no indication that they're not planets, and we have strong reason to believe they are planets, we haven't been able to follow up and confirm them. In fact, we're letting the community help out. On the other hand, our internal estimates are that on the order of no more than about 20% of our candidates are false positives. There's an independent paper out there by Jon Jenkins who estimates our false positive rate is closer to 10%. And there's a question in the back.
Your sample is biased by the bandwidth you look at?
Not really. We sample stars that are M dwarfs that are about half the size and mass of the sun. So the coolest main sequence stars that are burning hydrogen, out to early A stars, which are twice as big as the sun. And the reason we restrict ourselves to that range, which is very broad, it covers almost the full spectrum of main sequence stars, is that our primary mission was originally 4 years, and by the time, if you look at larger stars than the early A's, the habitable zone is too far out for us to collect enough transits in our primary mission. So we are volume limited, or it's a magnitude limited survey. So we go from about 9th magnitude to about 16th magnitude. And we've got lots of G's, lots of F's, lots of K's, 3,000 M stars, the brightest of which is 10th magnitude. So, and then at the same day that we announced these candidates, we also released all the data for the first 120 days on approximately 180,000 stars. We announced the confirmation of 6 transiting planets around one star, Kepler 11. So this is a very compact, very quick planar system. Yes?
Is there an official RV follow-up program for the candidates that make sense to do RV follow-up?
Oh, yes, we do. We have a very active follow-up observing program. People like Jeff Marcy, Bill Cochran, Dave Latham, and other people helping out. We use a suite of assets, including CAC, to do RV follow-up. But we also do high spatial resolution imaging to help us out as well, and some other measurements. So.
Might mention what RV follow-up.
Greater velocity. So I'll talk about this a little bit later, but please remind me if I don't. Okay, so let me go on. Okay, so this is the folded light curve for Kepler 10. And it's 1.4 Earth radii, it's in a 0.83-day period orbit, and this is the model fitted to the data. And the transit depth is 0.00015, so this is 150 parts per million. So this is pretty darn good. No AC photometry this good ever. So Kepler is really performing phenomenally certainly much better than my worst expectations, my worst fears in working with this program for over 16 years. Watching them design and then build the instrument, test it. So we are doing extremely well. Now, just to give you an idea, before Kepler, we had discovered about 70 transiting planets. Now, the first one was discovered in 2000, HD 20945 AD. That was the first planet discovered that happened to be transiting. The first planet that was discovered around a main sequence star was 51 Peg in 1995. It took about 5 years before we actually found one that was transiting its star. Up to that point in time, some people were saying, well, maybe these aren't stars, maybe these are just substellar companions that are formed in the same way that binary stars are formed. They really aren't planets. But once we started detecting transiting planets, all those arguments fell away because we clearly saw, once you got transits, you get the size of the planet, you've got the mass from radial velocity where you're measuring the reflex motion. The radial velocity is the velocity of a star along the line of sight by looking at the spectrum and watching it get red and blue shifted. So you put those two things together, you get the density. So most of these planets detected before are closer in size to Jupiter or larger. So Jupiter's about 11 times the radius of the Earth. So these are Jupiter in larger size. Here's Neptune, and here's Cobra 7b. And indeed, most of the 500 planets are much closer in size to Jupiter than they are to Earth. In the last several years, people are pushing down with radial velocity to detect super-Earth, things that are up to something like 4 times the size of Earth, between Neptune and Earth size. So we've seen a rapid revolution in this brand new field. Because of course, when I was in grad school, nobody was doing this, and the few people that were retracting their claims. So exoplanet science communities have to be very conservative in broaching this subject, coming to the fore with these discoveries. But we're seeing lots of productivity with radial velocity campaigns, and now with transit surveys coming online, it's getting even better. So last year we released the first 44 days of data, and we released identities of about 700 candidates. These are 305 that we released to the world. And you see we're pushing down with Kepler down towards Earth size. And we're also pushing out in terms of the orbital period because both radial velocity and transit surveys are more sensitive to planets that are closer in to their parent star and to larger or more massive bodies. So we only had 44 days of data, so we could estimate, because we have more data than we were releasing, the periods of these objects out to about 100 days. And then beginning of this month, boom, these are the rest of the candidates that fill in the 1,235. So we're pushing down to planets that are smaller than Earth size and pushing our periods out as we accumulate more data. So this is extremely exciting to be a part of all this and to see this happening. And lots, I think if I were on the sidelines, I'd be cheering too, because it's just great. It's phenomenal. So this is the changing picture of extrasolar planet science in near real time. Okay, and so the other thing to do is, since we know the mass of these stars, or have estimates for the mass of these stars, and the effective temperatures, and the sizes, and the distances that we can estimate the distance to the planet in its orbit, and then we can also estimate the equilibrium temperature of the planet. So this is a plot of the equilibrium temperature versus the size. So things we're really interested in are down here in the habitable zone, but because we're only looking at short periods so far, the habitable zones for most of our stars are further out. So if something's in the habitable zone, which the 54 candidates we've talked about are, those are largely habitable zones of smaller, cooler stars that have much shorter orbital periods in their hab zones. Yes?
Can you say something about that one that's all the way down by 0 relative to Earth size?
Well, this is not 0 down here. So this is 4, 3, 2, 1, and this is
What's the scale?
yeah, it's, I'd have to look at that. It's on our list, but I think the smallest candidate we have is about 0.7. So this is 0.9, 0.8, 0.7, 0.6. There may be a 0.5 there, something about half the size. Okay, so now I'm going to switch over and talk about how we process this data to actually make these detections in the first place. So this is the science pipeline. This is how we turn pixels into planets. So here's an image of a star. In fact, this was a star that has a known transiting planet that was discovered the year before we launched in 2008. And we launched in March of 2009. This is P7b. It's very bright. It's about 10th magnitude. It's actually saturated and bleeding slightly because CCDs have a finite well depth. So if you collect too much charge, they start spilling like ice cube trays. Okay? At any rate, the first thing we do is we have to calibrate the pixels. There are a number of on-chip artifacts that we have to deal with, and you want to put the data back on a linear scale where you want to know how many photoelectrons you collected in each frame and each pixel. And so you have to correct for things like nonlinearity. You have to correct for the fact that we don't have a shutter. You have to correct for the fact that there's a black level or bias voltage that is a function of where you are on the CCDs. All that kind of stuff. So the first step in the pipeline is to process the pixels to calibrate those. Once you've calibrated the pixels, then you can actually do your photometric analysis where you essentially sum up the pixels underneath the image of each star to estimate the brightness. At the same time, you also measure the location of the star. You measure a centroid. This proves to be very important in terms of false positive rejection. And it's also the reason why, one reason why CoRoT has not proved to be quite as productive as we all hoped that CoRoT would have been. CoRoT is a 40 centimeter transit survey. Well, it's a telescope that's 40 centimeters in low Earth orbit, set up to do astroseismology and detect exoplanets. And they were launched in 2007, and to date they've detected 15 planets, well, 2 of which are brown dwarfs, so 13 planets, which is a great disappointment. But in part, it's because they do their photometry on board. They don't measure the locations of their stars. Why this is important is because we've got large pixels. When you're doing transit surveys, you want a lot of sky. So our pixels are 4 arc seconds on a side. You can have a lot of stars in 4 arc seconds. And so if your target star has a dim background eclipsing binary nearby, that background eclipsing binary is diluted by the foreground target star. And so rather than seeing a 50% drop in brightness for an eclipsing binary of 2 equal components, you might see a 0.1% drop in brightness or a 0.01% drop in brightness. So what we can do is, in the pipeline, is detect Keplerian clocks, things that look like regularly spaced negative pulses. And eclipses look the same as transits once the stars degrade to a certain extent. So we expect a large number of false triggers on background eclipsing binaries. But if you measure the position of the stars, then what you'll see for background eclipsing binaries, in almost all the cases, it's going to be slightly offset on the sky from your target star. It's like having 2 weights on a balance. And if you take the star dims, you're taking a little weight off here, and so it tips this way. So you'll see a shift in the location, the measured location of the star on the sky, that's correlated with the transit. So you'll see a shift in transit from the baseline out of transit location of the star. Proves to be a very powerful technique for identifying blends where you might have a background eclipsing binary. Now, on the converse, it could be that you have a stable background star and the planet is really transiting the target star. You'll see the same effect. You'll see a correlation between the photocenter motion and the photometry. What this is a yellow flag that, gosh, we've got to do a little follow-up. So one of the most important things we do for follow-up for such cases is we get high-resolution, either speckled or adaptive optics imaging on these targets, so we understand what the distribution and brightnesses are of stars that are near our target star that are well within, well within the scale of a couple of pixels of our star. It's below the resolution of our targets.
Where do you get that data from?
Let's see. We get speckle at the WIN, and then Andrea Dupré is doing the adaptive optics, and I forget exactly where we're doing that. But
From the ground.
It's from the ground. Yeah. We also have some follow-up with Spitzer and some proposed follow-up with HST. Anyway, so once you understand what the stars are that are near your star that we don't know about beforehand because they're not in our original catalog, or you can't distinguish those stars in our images because they're too coarse, then you can actually interpret the centroid shifts and tell whether it's which star it is. So the centroid will always move away from the source, so it provides you with a magnitude and a direction from the baseline position, and so we're able to sort these things out. So sometimes it turns out to be a planet, sometimes it turns out to be a background eclipsing binary. Now the next step in our process is the hardest one, I think, because it's the hardest to get working as well as we like, and that's what we call pre-search data conditioning, where we identify and remove systematic errors. So it turns out Kepler is much like any other instrument that's a couple of orders of magnitude better than anything in its class before, and that is that once you've invented the world's best photometer, you've also invented the world's best thermometer. So it's very sensitive as a photometer, but it's also very sensitive to its thermal environment. And although we're in a very benign Earth trailing orbit, there are still thermal changes on board that are important when you're looking at the photometric time series. So I'll talk about that a little bit later. And then we've got the corrected light curves that we send through transiting planet search, and that's where we look for the periodic pulse trains. Once we identify what we call threshold crossing events, because they're not planets yet, things that look like they have statistically significant signatures that are correlated or look like transiting planets, then we subject those to a suite of diagnostic tests. One of those tests is to look at the centroid shift that we measured up in photometric analysis. We also look for things like we analyze the depth of the alternating transits to see if there's a significant difference between even and odd that would be indicative of an eclipsing binary with slightly different size components. We look for small changes in the intervals between the even and odd transits, because you can have a slight elliptical orbit of two equal components in an eclipsing binary. And we also remove or mask off the first transit signature we see and look for additional planets. That's very important because it turns out that about 20% of our stars that appear to host planets host multiple transiting planets. So we need to be able to detect multiple transiting planets. Indeed, the largest such system we have is Kepler 11, where we have 6 identified transiting planets in one system. Yes?
Are what you call candidates, have they been through the validation process?
They've been through this.
Remember words kind of confirm and validate.
Right. Okay. Well, we talk about 2 things. Data validation is our pipeline that furnishes a suite of diagnostics to the science team. We use that to rank and prioritize the candidates for the follow-up observing. And part of that is, what kind of stars. Because some stars you can't do good radio velocity measurements, like early stars, A stars, and they're too hot. They don't have enough features in their spectra. And so all the candidates go through this process. Then it becomes more of a person process where we have people that actually fit models that are have more sophistication than the ones we're fitting in data validation, where we extract the physical parameters of the system. So all the candidates have been through the system, and none of them have failed outright any of the tests that we perform internally, either in the pipeline or the other tests that people do in the science team afterwards. But those candidates are in various levels of maturity with respect to they have RV taken or even a reconnaissance spectroscopy to see whether you see double lines that would be indicative of an eclipsing binary from the start or something else funny going on. So you really have to look at the tables in Bill Baruchi's paper that's on AstroPH actually to learn the details about each candidate and how confident we are that it's a planet. So we have several levels. Yes?
So it's too early to talk about Planet Zoo, or is that?
Oh, there's a Planet Zoo. It's called Planet Hunters. So in terms of people actually looking through these light curves to identify planets on their own. Yes?
Is this pipeline, or is Kepler sensitive enough to detect large moons around?
Yes, it is. Our pipeline is not set up to detect those automatically because they're not evenly spaced periodic signals. So, but we do have science team members who are in a working group that are working on that. Okay, so just to give you an idea of what the data look like, this is a highly stretched clipped image, so I can show you the artifacts we have to deal with. So the vertical lines here due to the fact we operate without a shutter. We integrate for 6 seconds, and then we read out. It takes half a second to read the whole CCD out. So a pixel that's here for 6 seconds and travels down and hits that star on its way out, so it gets up light from all the sources below it. At the same time, a new pixel is being read into place to sit there for the next 6 seconds, and it sees all the targets above its locations for the integration. So the first order, the smear tails are uniform and constant along each column, but they vary over time and vary from column to column. So we have 2 special regions we use to measure that and subtract it off as part of the pixel level calibrations. The other feature that's you can see are these horizontal features. Those are caused by the clock signals driving the fine guidance sensors that are in the corners of our focal plane, and they're causing small DC offsets when each of these pixels is being digitized through the analog to digital converter. And it's a synchronous system, so this represents fixed pattern noise that we measured before launch. We confirmed that it was still the same on orbit, and we model and remove as part of our calibrations. So, and then we're focusing in on one star. This is P7b, and you see we essentially only send down about 5% of the data because we can't afford to store it on board. Yes?
This is a trade-off because the telescope doesn't move. You said something earlier that the telescope doesn't move. So if it doesn't move, you can't track it, so the stars move on the focal plane.
Oh, no, the stars don't move on the focal plane. So the fine guidance sensors track and take out the aberration to first order. So
then why is this streaking?
Oh, because you're reading out the CCD and there's no shutter. So you're moving the charge down the column,
Oh, I see, okay.
but light is continuing to fall on the sensor.
No shutter to increase your integration cost.
No shutter, because we couldn't afford to build one that had high enough reliability that it wouldn't. You could guarantee it wouldn't fail open or closed, right? It would be a single point failure, right? So, and micro shutters hadn't been invented yet. So James Webb Space Telescope will have micro shutters. That technology didn't exist when we were building Kepler. Okay, so we only store about 5% of the data. 6 million. Yes.
But now jitter is important because
Yes.
you're summing pixels.
I'll talk about that a little
Okay.
bit. But yes, there are a number of systematics, and that's one of the principal systematics. It was what we thought would be the dominant systematic. Our pointing precision is required to be 0.09 arc seconds, 3 sigma in 15 minutes and longer. And our pixels are 4 arc seconds. So to 3 sigma, we're talking about 100. We're talking about 100th of a pixel. I'm sorry, 1 sigma is about 100th of a pixel or so. So our pointing precision actually really good. It's comparable to Hubble's. And it turns out that the pointing jitter is not such an issue for the precision that's important to us. It turns out to be other things. So I'll talk about that in a little while. So here's transient point search. So to motivate this, you have to understand what beast you're dealing with when you're designing a detection algorithm. And this is these are measurements of the sun over about a 4-year time span from SOHO. We see that we start out in 1996 at near solar minimum. You see the rotation of the sun, because there are some features on the sun that you can see modulating the output, the irradiance. Over time, the sun rotates average period of 27 days. So you can see that in the data. And then you see spots starting to erupt as you approach solar max. 2 things you can notice from this is, well, at least one, and that is it's not stationary. And the other thing you notice, it doesn't look like white noise. So you need a detector that is adaptive. It can adapt to the changing conditions of the observation noise you're dealing with, and that can deal with colored noise or non-white noise. So those were the luckily back in the 60s, people had worked all this out. So at least if you're talking about filtered Gaussian processes, there are optimal detectors. The optimal detector is basically, it X is your data, your time series. What you do is you project that onto your signal of interest, but you have to account for the correlation structure of the noise, and that's what this correlation matrix R is. So if the data are white, then R inverse just evolves down into 1 over sigma, and you're just taking the dot product of the data with the signal, and you're normalizing it by the noise, sigma. So you're just looking to see how parallel your data vector is with your signal vector, and if they're co-aligned, then you say, hey, and it's got a large magnitude, then you say, hey, I've got a strong signal. That's basically all this is. So there's a normalization factor here that turns out to be the estimated signal-to-noise ratio of your reference signal. So that puts this test statistic on a sigma in terms of sigma. So you're talking about a 7 sigma detection, a 3 sigma detection, whatever. Now, if that's higher than your threshold, then you say you have detection. If the noise is stationary, you can actually transpose this into the frequency domain, and this provides a little more intuition, at least for those people like myself who like Fourier stuff. And in this case, the real meat of this is that what you're doing is you're multiplying the Fourier transform of your data with the Fourier transform of your signal, and you're normalizing it by the power spectral density of the noise. So this is what this looks like. These curves here on the right are power spectral density estimates for the sun based on that data I showed you earlier. And you see there's a lot more power out here at long time scales, at short time scales. And these are basically power spectral density estimates of an 8-hour transit and a 12-hour transit. So the reason why this works for Kepler is that for sun-like stars, transits are short, and spots rotate in and out of view on time scales of weeks and longer. So we have a time scale or frequency separation between the 2 signals. It's kind of like listening to barbershop quartet, for the tenor to be singing his solo. If the bass and the baritone stopped in the bar on their way, and they're singing out of tune, and they're singing loud, too loud, you can still hear the tenor because your ear can separate the frequency space.
But what about for M dwarfs, John?
M dwarfs
Isn't the
are
frequency a bit higher for those rotation rates?
Well, in general, they're older, so they're smaller and they spun down even more. But they are more active, so not all, so each star is its own thing. You have to estimate or characterize the noise for each star independently, and that's what we do. So wavelets are a natural choice because wavelets are a joint time frequency representation. And we've chosen a filter bank implementation. This is a lot like a graphic equalizer you might have with your stereo system. where the lights tell you exactly how loud or how much energy or power there is in each of those channels at any particular point in time. And what we do is essentially we convolve the data with a bank of filters, and each filter picks off a different region in the Fourier domain, and it's orthogonal, which is really nice. Okay, so what that allows you to do then is to look in each of these channels to estimate the noise power in that channel, and then you can whiten the data, which is essentially what you want to do. If we go back here, is that whitener, or the power spectral density, to do your detection, what you do is you divide your data for a transform multiplied by the transform of your signal by the inverse power spectral density of the noise process. So it means stuff out here isn't going to get much weight. Stuff down here gets a lot of weight. So this is where we're able to detect stuff, is in this region. So that's really what it says. So this is a signal flow diagram that shows the bank of filters, and then the data comes in here, and each channel has its own time series coming out. We estimate the noise power. That's just, we have an analysis window that's just RMSing the stuff going through it. And then you convolve it with a corresponding channel signal from the reference transit pulse. You're correlating that in each channel, and then use Parseval's relation in this frame, this wavelet frame, to build up your statistic. So it means that in MATLAB, that's only about 20 lines of code. It's very efficient. Okay, so here's Kepler-like noise plus transits, and this is SOHO data with noise pertinent to Kepler. And there are 4 Earth-sized transits here. Can anybody see them? Sure. Sure? Yeah. On this scale, an Earth-sized transit is 0.1 watts per square meter, so it's a fifth of this major tick. So I guess we all see them, but I don't know many of us could actually point them out by coming up here and pointing on the screen. But if you apply this wavelet adaptive match filter, these are the single event statistics as a function of time. The blue data is with transits, the red is without. So we see blue spikes where the transits are located. Then the idea is to fold the data. If you choose the right period and you fold the data and stack it on top of itself, the transits are aligned. They act coherently, but the noise doesn't. So it allows you to build up your signal noise ratio. So in this case, we get a total signal noise ratio of about 11. So this is a clear detection. Our threshold should be about 7 sigma to reject statistical false alarms. Okay. And then you can, and this is a projection. This is the maximum statistic you get for each trial period. But if you look at this trial period as a function of time to first transit, there it is. Okay, so this is a simulation, but it's using real SOHO data. Now this is real data. This is a much deeper transit than Earth. You can actually see it easily by eye. But here's what the correlation time series looks like. And you see the data in between the transits looks quite white. And this is the normalization time series. So this is the other part that goes with this. We estimate our combined differential photometric precision. This is in ppm, so this is 100 parts per million for this star. And then down here are the single event statistics in sigma. So each of these events is about a 30 sigma event. So this is an illustration of how this works with the signal you can actually see by eye.
What creates the negative dip?
The negative dip here?
Yeah.
That's because you're correlating the pulse. It's like going into a funhouse where the whitening filter makes the data look white, but it's distorted your transit. So it's like going into a funhouse looking for a friend's face, but you know the shape of the mirror, so you know you can predict how your friend's face will be distorted. But you're moving, you don't know where these things are, so as you move this transit mask across your whitened data, you get your peak when they're centered on top of one another, but then you get this ringing because your whitening filter is a high-pass filter, and it takes a transit and accentuates the edges. Okay, and then you fold it, and here's the period. And then here's the phase, and there it is at 13 days into the data. Okay, I'm going to turn my attention now to pre-search data conditioning. Yes?
Plus you can also make predictions and tell when you should be seeing it in the future and go back and see if you're right. That's another way of confirming, you know?
Well, it is. It's something that we do outside of the pipeline. So the pipeline furnishes us with candidates, and we keep track of those to see what's happening. But yes, we do that. So pre-search data conditioning often does a good job. So these are 2 stars. The red is the original light curve or flux time series, and the blue is what comes out of PPT. We've got a number of operational activities that can impact the photometry. Pointing tweaks where we had larger than expected drift in the pointing at the beginning of the mission before the flight segment actually tuned up their algorithm. So that we injected offsets intentionally to keep things aligned, because we only send down the postage stamp. So if we wander outside the postage stamps, bad news, you don't get your data, you don't get your planets. And we had some safe modes, and during these early safe modes, we turned off the photometer so it cooled down. Principal heat load are the CCDs and the associated electronics. So turn the thing back on and it heats up. Well, even though we had, quote, equilibrium, you can still see the thermal signature 4 or 5 days into the data. So our algorithm has to deal with these operationally induced thermal signatures or other signatures in the data. And also we have radiation events that cause near instantaneous drops in the quantum efficiency of individual pixels by about 1%. It seems to be quantized. And that causes drops in step discontinuities in the time series that you can see here and here. So PDC has to deal with these things and try to correct them. In these two cases, it's doing a pretty good job. But I'll show you an example where it's not. So the blue light curve, this is an eclipsing binary. It's got spot-induced variations on it. Very interesting astrophysically. But what we do with PDC is we're handing it a bunch of measurements of systematics or things that are associated with systematics, like pointing jitter, like the measurements of the pointing over time, and the focus change over time, and the temperature over time of the detectors, that kind of thing. And it finds a linear combination of those things that reduces the bulk RMS of the blue when you subtract it off, but it does a lot of bad things too, this light curve. As you can see, the blue light curve does not have all this hair and fuzz on it. Now, this hair and fuzz is real stuff going on in the photometer, but a straight least squares fit really doesn't know the difference. So that's what is motivating us to find another way. So the problem with least squares approaches is they attempt to explain everything about the light curve that you give it, about the thing you're trying to model, about the data. And it doesn't, it doesn't just try to explain things that it can explain well. It doesn't know the difference. And there's no simple way that least squares fits and put on the brakes. It can't understand that a change in pointing of 1 millipixel can only induce at most 8.1% change in a light curve. It doesn't know that. So it's happy to say this 0.1 millipixel change in position can explain 10% change in flux. So, so it's not like taking a puzzle out of a box where you see the picture on the box, and you open it up and there are only 20% of the pieces there. Least squares is happy to work with 20% of the pieces and put it together so it approximates the picture on the box. But it's really doing things that you don't want it to do to your data. But this is what least squares is really good at. It tries to explain everything it can about the data, and oftentimes it can distort the fit so that it gives you a good approximation, but it's also introducing a lot of noise or artifacts. So the problem is to find a model that best fits the data. So I don't want to bore you with a lot of math, but here's our estimate of what the data should be. This is our model y hat. We've got a linear model, so H is a design matrix. Each column is a vector like temperature change over time, pointing change over time, whatever. And theta are our coefficients. So we want to take a linear combination of the vectors in H to try to explain the data y. What we'd like to do is bring in side information, because the power of Kepler is that we have up to 170,000 targets. And on each detector, we have approximately 2,000 targets. So we can look at the behavior of the stars as an ensemble to try to constrain what the coefficients are for the fit. And I think a really good way of doing that is to use the maximum a posteriori approach. And what that is what you're trying to do is you're trying to maximize the probability for a given set of coefficient values given the data that you're handed. Now that's hard to deal with, but you can rewrite this using Bayes rules, but what you're doing is you're maximizing the likelihood of the data given the coefficients scaled by the probability that those coefficient values exist, right? So this term POC, that's the prior probability of the coefficients, and that's something we can derive from the ensemble of light curves. And this first term, if you ignore the fact that if you take it out of its Bayesian context, this leads to least squares. So this is an augmentation of least squares to bring in side information, which means that if you adopt a Gaussian prior, and I'm not recommending this, this is for pedagogical purposes. If you adopt a Gaussian prior and you work through that, then you get a very simple expression in linear algebra terms for the solution. And that estimate is this, and it has two terms, one that's associated with least squares, which are these things, and one that's associated with the priors, which are these things. So for uniform white noise, then this becomes this, where you essentially have the variance of the data or weighting the prior against the fate that you put in the data itself. So as the variance of the data gets very small, the map estimate trusts the data, and you end up approaching the maximum likelihood or least squares estimate for your coefficients. On the other hand, as the variance gets very big, the map estimate says, I don't trust my data, I trust my prior, and so the solution will approach the mean value for the coefficients themselves. So what you need to do with this approach is you need a way to characterize the covariance and mean of the coefficients. So I'm going to walk you through how we might do this. Now this is a correlation map of 2,000 targets on module 2.1, which is one of our most thermally sensitive modules, and this is and red is 1. So it turns out that the vast majority of these targets are all doing things that are highly correlated, plus or minus correlation coefficient of 1. So it means that you can take 1,400 of these, as I did, and do an SVD and then say how many components explain most of the variability. It's about 10. So the stars that are not dancing along with the other stars are those variable stars that are doing their own thing, where they're dominated by stellar variability, intrinsic stuff going on in the star, not by instrumental systematics. So the idea, so here's the first term in an SVD decomposition. You see all this hair? That's caused by a heater cycling on and off of reaction wheel assembly 3-4. This component was getting more and more shade over time during this period of time. And when the heater kicked on, it would heat up about 5 degrees C and then turn off. And then when the temperature drifted back down, it would heat up again by 5 degrees C and turn off. And as it got more and more shade, it was turning on more and more often. In fact, at the end, it was just cycling on off continuously. This 5-degree change in temperature on a box on the outside of the spacecraft, which is supposed to be thermally isolated from the telescope, is causing approximately a 1 micron change in the distance between the CCD detectors and the primary mirror. So we can see this easily by eye, not just, and we can see it at the pixel level. So this is a very sensitive instrument. It allows us to know a lot about the instrument that we don't want to know about, right? And the other features you see are we desaturate the reaction wheels every 3 days, and that gives you these humps. Because for whatever reason, that changes the shape of the telescope. When you do that, you change the temperature of various components. And as the sun appears to rotate about the barrel of the telescope, then the thermal situation changes, and we get large changes in focus when the sun is pointed at the back end of the telescope, because it's in orbit about the sun, pointing at one field of view. So during the summer, we're pointed away from the sun, and the sun can see the bottom of the back end of the spacecraft. And on the other side, we're over here. So anyway, so this is the first component. It looks like a lot of the systematics that we've learned to love as one loves, I don't know, certain cousins that get drunk at your wedding. At any rate, but this is, if we plot this coefficient goes with this term when we fit all the light curves. These are 2,000 fits, one for each star. And this is what that coefficient looks like as a function of Kepler magnitude, and you can see there's structure in here. So this gives us information that we can use to inform the prior. In this case, this coefficient is a function of the magnitude of the star, and the width of the distribution is a function of the magnitude as well. So we can use those to, in this little toy sort of demonstration that this will work, and establish Gaussian priors for each of these coefficients based on these scatter plots. So now, why would you expect them to be Gaussian? You might look at this and say that's not Gaussian at all. If you look at it, and they are. But this is just sort of like just to demonstrate that we've got something going here. We're developing an empirical method to estimate the PDS, and so this is an example of one of our empirical PDS. But that's under development now. What I can show you today, though, are the results of doing this map using these Gaussian priors. And so here's an R-Lyrae star. These stars explode once every 12 hours or so. They're very interesting. They're related to the Cephiids, so they establish the distance scale to other galaxies. They're standard panels, even though they explode every half day or so. And least squares fit provides you with a fit that's the green curve, and it's got a lot of noise on it, apparent noise on it, that if you subtract the green curve from the blue curve, bad stuff happens, right? What you can see is that over time, this thing is getting dimmer. Now, that's not what the star is doing. The focus is changing over time, and the images are getting more spread out, more blurry. The map recognizes that, and so the red curve allows you to correct out for the focus, the broad, long-term focus shift, without introducing a lot of extra noise. Here's another example. This is one of the typical stars that's very quiet, that's on this module. It's dominated by systematics. And in this case, the least squares fit and the map fit are comparable. The map fit trusts the data, but the data are close to where, coefficients are close to where they should be anyway. So This appears to be a very good technique to deal both with quiet stars. For the most part, we're doing a good job at quiet stars, as well as for the more astrophysically interesting stars that stick out like sore thumbs when you don't deal with them correctly. So this is that other target I showed you earlier where we were doing a poor job with least squares fit theory. But again, the map recognizes that this star is variable and it trusts the priors over the data, so it does not reduce the, it doesn't attempt to do this crazy fit to reduce the bulk RMS, which is what least squares is trying to do. Okay, so conclusions. Kepler mission is returning a wealth of exoplanet science, and I didn't have time to talk about today, but also astroseismology, the study of oscillations and pulsations of stars. And we really are revolutionizing that field. In fact, there are many more publications coming out of Kepler for astroseismology than there are for planets. And that's because people have been waiting for decades for something like this to get such contiguous, long-term photometric time series on variable stars so they could actually study the pulsations of the stars. The great thing about astroseismology is that if you study the tones, because all the stars are ringing like bells, the sun rings typically it's got a coma frequencies, but they're about 5-minute time scales. But you can study the intervals in between the tones and frequency space, and those are related to the size of the star and the mass of the star. So you learn something about the composition and structure of the star, and you can also get, for our brightest stars, you can get the radius to 1%. There's much, much better you can get from any other technique available today. Our stars are far away, relatively speaking. They're very close in other ways, but 1,000 to 3,000 light years or something. Okay, so astroseismology is very exciting. In fact, this, and then PQRs, these RLI rays are very exciting because there's, if you see this modulation of the envelope, that's called the Blaschko effect. And that's a mystery. Nobody knows what's causing the Blaschko effect, this modulation and then intensity. And they come in all kinds of time scales. Most of them are on times of 10 days or longer. Nobody knows what's causing that. That's been known for 107 years or so. But nobody's known. And our astroseismologists believe that Kepler data will allow us to crack this mystery and solve it. So that's all very exciting. What has worked out very well, although we are tuning it up, because data aren't perfect, is the wavelet-based approach that's allowing us to detect small planets in the presence of time-varying non-white observation noise and stellar variability. And this map approach looks very promising because we can use it to augment the current co-training approach in PPT and bring some reason to the coefficients that we're fitting so that we can reconstruct the physical constraints underlying what's going on between the perturbations like pointing and focus change on actual measurements and develop an implicit model. And it promises to improve our ability to identify remove instrumental signatures while preserving intrinsic stellar variability that's of such great interest to exoplanet science as well as to astroseismologists. So that's why I came here today to talk to you about it, and I'd be happy to entertain any questions you have at this point. Yes?
Early in your talk, you showed some scatter plots relative to Earth size or period. I think there was a temperature.
Yes.
And it was just in the back of my mind that there might be theoretically some first principles calculation for if there were a real planet in that coordinate space, there'd be a probability of detection that could get calculated.
Yes, in fact, that in terms of the two things going on. One is that you can calculate for each of the candidates and calculate what the geometric probability of allowing it to see the transit is in the first place, because how big the star is, how wide it is. The other thing we know is that you have a noise estimate from our wavelet-based technique that provides you with the S and R of that candidate, and you know what the threshold is, and so you can estimate what the probability is that you would have seen that candidate for others like it across your data set. So if you look at Bill Berkey's paper that's posted in Astro PhD, we've made both of those corrections, and so the resulting estimates are that 7% of the target star sample have Earth-sized planets, things that are smaller than 1.25 Earth radii, and then like 7 or 10% have super Earth-sized planets go from 1.25 to something like somewhere between Neptune and Earth. I've forgotten the you start seeing a drop off in the fraction of stars that host planets when you get to their larger size. Which is very interesting. But yes, you can actually look at it and use the data itself to understand what that is.
Yeah, my thought was something quite naive, which was like to divide these candidates by those probabilities. Planet distribution.
Right, and so in Bill Berkey's paper, this is the first by looking across all the targets and saying how many targets would I have been able to detect each of these candidates. So and bin them by size and by spectral type and stuff. So there are different cuts to make. It's just the first cut because, of course, we're very early on in the mission. The Holy Grail for Kepler is to find an Earth-sized planet in the habitable zone of a sun-like star. So that means orbital periods of a year. And we're not. We need 3 or more transits to be at a point where we can reliably detect those objects, and so we're going to have to wait a little while longer so we can accumulate enough data to actually make the detection in the first place and then follow it up. There was a question earlier about follow-up, and so the one thing that's different about Kepler is that it's pushing us down into a regime of planets now down here where you can't do radial velocity. You can only establish an upper limit for what the radial velocity might be. You can't measure the radial velocity and get a mass unless it's very close, like Kepler 10, where we actually did get a radial velocity measurement and got a mass and then have a size. So what we're dealing with now is saying that you confirm a planet by radial velocity, you validate a planet by being very certain that the probability that you're being fooled by a background eclipsing binary or a hierarchical triple system, because you have multiple sources that have a binary and another star, or even more, but you need to reduce that probability down to a very small number. And we're using a blender analysis where Willie Torres and Francois Fresno are running a lot of models of stars, because if you have a hierarchical system, they're all the same age. And so you can constrain the masses and effective temperatures and things. And so they run through all the possibilities to find out how many configurations could actually cause you to see a transit-like feature when it's really an eclipsing binary in a multiple system. And indeed, that's how we've validated some of our planets that we've been to date. Kepler 9c. So Kepler 9 was the first multiple transiting planet system discovered and announced. This was last summer. It was 2 Saturn-sized planets, and then an inner, much smaller 1.6 Earth radius planet, much tighter orbit. That planet was not massive enough for the star to allow us to observe it directly using radial velocity, but we used this blender analysis with stellar modeling to eliminate or reduce the probability that we could be being fooled by a hierarchical triple system down to a level where we were confident enough to release it down. So the other thing you have to do is you have to reduce the confusion radius, the radius within which there could be an eclipsing binary in the background that's just too close to your target star to make the centroid shift stuff work, and reduce that down to an acceptable level. And I can't off the top of my head remember exactly what that was, but it was more conservative than I thought we were going to end up with. That it's on the order of less than 1% or so. So we want to be 99% or higher confident that these things are real and not false. Of course, we're going to get wrong at some point in time. Okay, yes, questions?
Maybe you said that in the procedure was input for the conditional distribution of the data given the coefficient.
Given the coefficient? Oh, well, if you that basically what you do is you substitute in the values for the coefficients into the Gaussian. And it just looks like least squares. So it's just the exponential minus, and then your data point minus the predicted data value squared normalized by whatever we know that certainty of the distribution. So that looks exactly like the likelihood function that gives you least squares if you take the gradient and set it to 0 and all that. Yes.
If you find the Holy Grail, it's the Holy Grail on the way to the next Holy Grail, which would be spectral information.
Right.
Which you want in the IR, which means you now have just lost half your resolution, right? Because your wavelength is now.
Well, Kepler's okay.
No, so what does it take? If you were doing the same experiment between 1 and 2 microns with the same or twice as large telescope, would you see it? What how do you scale the system?
Okay, so the grand scheme of what NASA is trying to do on its quest to find light elsewhere is Kepler is the census taker, so it's going to define the frequency and distribution and prevalence of Earth-sized planets in the habitable zones of stars of different spectral types. And TPF, terrestrial planet finder, which is kind of a misnomer, is going to be, well, we don't know exactly what's going to be the pre-proposed architectures, but the idea is to be able to image and take spectra of the planets to look for biomarkers in the atmosphere to constrain that. That's probably decades away now. But right now that's what people think it's going to take to do the job. So Kepler's job is to define the search space for those follow-on approaches so that we can actually scale them appropriately and cost them and get them going. And you've been waiting patiently.
Multiple planets in the stars, so that see that phenomenon commonly?
Well, that's one of the greatest surprises I've seen is so many multiple systems so early. If you look at the solar system from somewhere out there in the galaxy, right in a random position on the sky, if you see Earth transit, you have about a 12% chance of seeing Venus transit. So you could say, well, maybe you'll see 10% of the time. What we see is that about 20% of the target stars that have transiting planet candidates have multiple transiting planet candidates. So the system I talked about earlier, which I thought I had a slide in here to illustrate, Kepler 11 has 6 transiting planets. So if you look at the whole system, it's about, if you remember those old LP, old records, LPs, about this big. So the system is about as flat as an LP. The inner 5 are within orbit of Mercury. And that system is about as flat as a compact disk. So these are very coplanar systems, and one of the things that Kepler is doing very early on, which I didn't expect, is it's showing that multiple transiting systems appear to be very common. That indicates that the coplanarity of these systems is very high, so they're very flat. And this was something that was in deep question leading up to Kepler, because beforehand, with radial velocity surveys, you're sensitive to more massive planets generally. A lot of the giant planets are in highly eccentric orbits, and the ones where they detect multiple planets are often there's a lot of dispersion in inclinations. So if that proved to be the rule for smaller systems, then that would indicate that it seemed to imply that our solar system is kind of weird because we only have dispersion of a degree or so. So we have some wackos in terms of Pluto and Mercury and stuff, but it appears that nature loves to make multiple planet systems and it likes to form them in planes. So this sort of boosts our confidence that the general model for how planets form with further planetary nebula collapsing into a disk is right. And a lot of these systems that we've seen with radial velocity that high eccentricities and dispersions and inclinations are probably driven by stochastic events late in the life cycle of those systems. Okay.
I don't know if this question makes any sense, but are you able to find the properties of the hot star?
We do. We had a stellar classification program that Dave Latham carried out with his group that lasted for about 4 years prior to launch, where they took basically multi-channel photometry, and they used the Sloan filters and some others of our whole field, in fact, more than our field, because we ended up moving our field after they got started. But they have delivered us a catalog with effective temperature estimates and log Gs and all the information that they could find in other existing catalogs. It has 4.5 million objects in it that fall on our silicon. And so we have going in estimates of how big these stars are and how bright they are and how hot they are. And then when we detect a planet, then we do follow-up because you really want to do this using spectroscopy, not using multi-channel photometry. So although it proved to be very, very good, one of the biggest questions is how can you separate the giants from the dwarfs, the things that are burning helium from the things that are burning hydrogen still? Because we want the small hydrogen burners. And there's this question, can you do with photometry? It turns out that 90% of the time, the Kepler input catalog got it right. So it did a really good job, much better than I expected, and many other people, of discriminating between giants and dwarf stars based on the photometry. But one of the first things we do with follow-up is, did the kick get it right? Is it the right effective temperature? Is it the right size? Is it the right gas? That kind of thing. Yeah. Okay.